Hi, welcome to lesson 5. Here we're going to look at the properties of definite integrals, make sure we understand why they work, and apply them. Okay, so to discover some of these properties, let's go ahead and take a look at these two functions graph below. Go ahead and copy down the graph here and then answer each of these four questions. Each of them will lead you to discovering a property that is true for all definite integrals. All right, let's start with number 1. This one's very straightforward. Since the interval of integration is from a to a, it's very clear that we're not going to accumulate any area, and therefore the value of this definite integral is going to be 0. And we can take away from this that anytime our interval of integration consists of 0 space, our definite integral will be equivalent to nothing. For number 2, what we want to notice is the, again, interval of integration. And this first integral goes from a to c, and so that's going to accumulate all of the area in this portion. And then the second integral goes from c to b, and so that will include all of the area here. And so if we want to write this as a single integral, all we have to do is allow our interval of integration to encompass this whole interval, and therefore it'll be from a to b. And what we want to take away from this situation is that if we have two integrals which are connected, in other words, the upper limit of integration in this integral is the lower limit of integration over here, then we can rewrite it as one integral that encompasses that entire interval. All right, for these second two, what I want us to do is take a look over here. And if you consider what occurs when you take the function f and add the function g to it, your y values are just going to be added on top of one another. So if we consider this point right here, if we imagine what f plus g will look like, well, here's f, and then if we add g, it's going to go up here. And so if you take the area underneath this point, you'd end up with all of this, which is simply this green line plus this red line. And so what we can say here is that whether you're looking at simply the area underneath this point, or you're looking at each of them independently and then adding them, it's the same thing. So what we can do here is instead of taking the integral of the addition or the sum of these two, what we can do is we can take the integral of each independently and then add those together. And the exact same reasoning leads us to do that for a difference between the two functions. We can take the integral from a to b of the difference of the two, or we can take the integral of each and then take the difference of those two integrals. All right, so there I've represented each of these situations with one expression where I've used, you can either do the sum or the difference of the two for these two situations respectively. One thing to keep in mind is that if you're going to go from a sum or difference of definite integrals to the definite integral of that sum or difference of the two functions, then you need to make sure that your interval of integration is the same for both of these before you can then add or subtract the two functions within the integral. Number 4 is pretty straightforward. If you consider the function f and you are looking at the area underneath the function f between the function and the x-axis, all of this area is going to be above the x-axis. So the definite integral here is going to be, a positive number. When you look at g of x, you notice that some of it is below, okay, so that's going to be counted as a negative area. And then this piece here is going to be positive, but we notice for this interval, right, that g is always beneath f. In other words, from whatever this point is to b, the integral of f is still going to be greater. And so it's very clear to see that the integral from a to b of f of x dx is going to be greater than the integral from a to b of g of x dx. And the reason this is that f is always going to maintain a greater value than g. And so when we're looking at the definite integral and we think about those products, because the product utilizes the value of the function at each of these points, since f has a greater value at all of these points, then it's the sum of those products is obviously going to be greater for f than it will for g. And so the reasoning here is that f of x is greater than g of x for all x in the interval from a to b. And we can take that and extend it, that if we have one function which is always maintaining a greater y value than another function, then obviously when we take the area underneath that curve, in other words the definite integral, that definite integral is going to maintain a greater value. All right, let's go ahead and take a look at just a couple of more properties, but all of these are very useful, and we'll see why as we move forward. Okay, so here's a full list of the definite integral rules and properties. You can find this on page 293. All the ones that do not have any of these green boxes are ones that we've already gone over in some way. So I'm going to go over those briefly, and then we'll take a look at the new ones. First one is that if our interval of integration does not encompass any distance, so from a to a or from any number to itself, then the integral can be evaluated and is equal to 0. Additivity, which refers to the interval of integration, so if one interval goes from a to b, and then we have the integral of the same function from b to c, then we can just write it as one integral from the lower limit of the first to the upper limit of the second, since they're, in other words, connected. The sum and difference, really nothing more to go over here. Again, they've written it with this plus minus to illustrate that it works for either the sum or difference. And then lastly, what's called the domination property, which is that if one of the functions is greater than or equal to another function on the entire interval, then when we take the integral of the greater function, it's going to be greater than or equal to the integral over the same interval from a to b of that lesser function. And similarly, what you can say is that if you have a function that's always greater than or equal to 0, then when you take the integral over that same interval, it's going to be greater than or equal to 0, which is pretty obvious when you consider that the area above the x-axis is going to be positive. All right, let's go to one of the more helpful ones here, which is that if I have the integral from b to a of f of x dx, what will that be equal to? Well, what you want to remember here is that we're considering, and I have this graph here, that b is greater than a. So if you're going from b to a, that means that when you look at, if you look at the Riemann sum, you'll remember that the change in x, delta x, is given by the upper limit of integration minus the lower limit of integration divided by n, right? And so here you would have a minus b over n. But b is greater than a. So a minus b would all of a sudden become negative. In other words, all those infinitesimally small dx's would be less than 0, right? They would be ever so minor, but they would be negative. And so when we computed the product, all those products would be negative, and then all of a sudden, all of our sum would be negative. And so this is, in other words, the exact opposite of going from A to B. And so that's exactly how we define it. It is going to be the opposite, or negative, the integral from A to B, which in other words just says if you switch the order of integration, then you're multiplying by a negative. This can be very, very useful. Next, we're looking at the constant multiple. So that's saying that if you have some function and you're multiplying by a constant, then you can factor out the constant. And if you think about this, the reason that is that if you have some constant, so consider your function here, and say you multiply it by 2, well, that means all of these values will double. That just means that the area underneath will double. And so it doesn't matter whether you take the area of the function that's been doubled, or you take the area of the function, and then after you've done that, you double it. In other words, you can factor out the constant. And that, of course, extends to negative values. So if you are multiplying a function by a negative, it doesn't matter whether you do that first and then take the integral, or if you factor out the negative, take the area, so for example, the area underneath f, and then multiply by a negative. It would be the same as multiplying f by a negative, in other words, reflecting over, taking all that area, which would then be negative area. All right, and last but not least, we have the max-min inequality, which says that if the max of f and the min of f are the maximum and minimum values of f on this interval, then, well, think about this. Look at f here. Its minimum value is right here, right? So if you use that minimum value as the whole function, to approximate the whole function, and you took the area underneath that, and I'll just kind of draw that here. If you took the area underneath this white curve, it would be less than the area underneath the green curve, because the value we're using of f is the lowest value on that entire interval. And that's exactly what this says here. It says that if you take the minimum value of f and you multiply it by the interval from a to b, right, so b minus a, that area is going to be less than the true area underneath the curve. And similarly, if you took the maximum value of f, right there, that area underneath that curve is going to be greater than, so max of f times b minus a will be greater than or equal to the true area underneath the curve. And it's important to note, first, that this is greater than or equal to because f of x could itself be a straight line, a horizontal line. And so that would mean that all of these would be equal to each other. So that's why we have to include the equal sign. And this is very useful because if you can find a minimum value of your function or a maximum value of your function quite easily, then what you can do is you can bound the true value of the definite integral, saying, you know, okay, I know the max, so therefore I know a value that's going to be greater than or equal to the true integral. And that can be quite useful. All right, let's go ahead and apply these rules and properties. You want to spend some time learning these, meaning that you understand each of them and you are able to sort of have them in your memory to pull out whenever you see a situation that looks like you could apply one of these properties. All right, let's try one. So what you want to do is write this down, and before you immediately turn back to your list of properties, I want you to analyze both of these integrals and ask yourself, what property do you think you might be able to use? Try and apply it on your own first, and then go back and confirm that that property is in fact the one you're using, and check your answer. Then go ahead and press play and we'll work through it together. Okay, so the first thing we want to notice, of course, is that all of these integrals have something in common. It's the integral of f of x dx, right? So what we're going to do now is look at the interval of integration and see how we can combine these two to end up with this. So we want our lower limit to be -5 and our upper limit to be -1. And we'd like to then, because we know this is the interval that we're trying to get, and we have two integrals, we're going to try and use the additive property, that if we go from a to b and b to c, then we can go from a to c. The only problem is that -5 is the upper limit here, and we want it to be the lower limit of the integral we're evaluating. So we need to rewrite this integral so that it goes from -5 to 3. And of course we can do that because if we reverse the interval, that means we just have to multiply by a negative. So if we reverse the interval and then we're multiplying by a negative, that will lead us to a value of +6. So to show that here, I've switched the limits of integration, and I know that this integral is equal to -6. So this integral is equal to the opposite of that, meaning this is going to be equal to -6, which is of course +6. Now, since I have this interval from 3 to -1, and this goes from -5 to 3, I can combine those two intervals and go from -5 to 1 simply by adding 6 and 4. And there you have that written out. One thing that might be a little confusing here is that 3 is actually greater than -1. And so you might say to yourself, well, this really makes no sense. I'm going from -5 to 3, and then from 3 to -1, which is sort of reversing the way that we would normally travel. And that's actually totally fine. If you thought about this and think about it as going from -1 to 3, okay, that would mean that you would have the area underneath the curve from -1 to 3. And what you would really be doing is then subtracting the integral from -1 to 3 from this integral. Well, what that would mean is that you would take 6 and you would subtract -4 because you'd have multiplied by a negative to go from -1 to 3. And so then you'd have 6 minus -4, which would of course still be 10. So all we really need to worry about is that the upper limit here is equal to the lower limit here. And so long as we've done that, we can connect the lower limit of the first and the upper limit of the second through addition. At this point, I want you to get a little more practice. So head to page 294, and at the very top of page 294 are some practice problems for you to work through. Try them on your own. You can actually do them sort of in your head if you want, and then take a look at the explanations in the book, and then we'll go ahead and we'll work on one more example before you head to the homework. All right, hopefully those went well. Let's go ahead and try this out. So show that the value of the integral from 0 to 1 of the square root of 1 plus cosine of x dx is less than 3/2. Go ahead and try this on your own first, and then we'll take a look together. All right, when we're looking to show that the value of something, this integral here, is less than some value, think about what that means. If we could show that the greatest possible value this can have is also less than this, well, then we've obviously shown that the value of this, whatever it is, will be less than this. And so in other words, what we're doing is we're looking for an upper bound for the value of this. We're looking for what the biggest this could possibly be is. And certainly, as we've seen with integrals, that if we find the largest value of our function, then we use that to approximate the function on the whole interval, then the area of that space is going to be an upper bound. It's going to be the maximum value that this could ever have, and will, in fact, in this case, be greater than that, because this isn't going to be a constant function. So we're looking for a maximum value of our function on the interval from 0 to 1. So we're thinking about 1 plus cosine of x here. And what this boils down to then, of course, is what is going to be the biggest that cosine of x can be on the interval from 0 to 1. Well, if you look at your unit circle, you'll notice, of course, that cosine of x starts out at a value of 1 when x is 0. And it then just gets smaller because cosine represents the x-coordinate as we travel around the unit circle. And so by evaluating our function when x equals 0, we'll be able to find the maximum value of our function on that interval, and therefore be able to find an upper bound for our definite integral. All right, so our reasoning works as follows. The maximum value of the square root of 1 plus cosine of x on the interval that we're discussing is the square root of 1 plus cosine of 0, because that's where cosine is going to be its maximum value, which is 1. And so this ends up being the square root of 2. And that means, by that last rule, the domination property, that means that the integral from 0 to 1 of square root of 1 plus cosine of x dx is going to be less than or equal to that maximum value multiplied by the length of the interval, right? In other words, this is the area of a rectangle with a height of square root of 2 and a base of 1 minus 0. And that, of course, is equivalent to the square root of 2. Now, the square root of 2 happens to be 1.414, so on and so forth, and of course that is less than 1.5, which is 3/2. And it's strictly less, which means that the value of our definite integral is less than 3/2. And so we've now shown what we were looking to, and we've completed our process. All right, go ahead and now complete homework 7.05.